Hi everyone, welcome to week six. Week six, so we are looking at the random sample statistic, common statistic like mean, median, right skew, left skew, the distribution. Then we'll look at the R application, central limit theorem, application of central limit theorem, and general samples, mean distributions in R. So a few practice in R. Okay, so first, let's do a quick recap. So sampling distribution. So we create the samples draw from a population of our interest. Um, yeah, yeah. The reason is we can't usually measure everyone in this population, so we can only have limited resources to draw the data from the sample. So that's for practical reasons. Then there is a key concept called IID, independently and identically distributed. The sample must meet this requirement for study purpose. So what is independence? What is identically distributed? Which was covered in the video lecture. Okay, and you can also look at one of the examples, some of the examples here. So next we will look at descriptive statistics. Okay, so the role of a statistic describe a way to condense the sample information. Because sample, if we get 1,000 samples, then we have to remember 1,000. Then we want to find a common probability of these samples. Say, for example, what is the average value of the student in taking the AB 1202? There was a 700 student. Then instead of remember the height of every student, then we want to find some common statistics to condense the information of the 700 students' height. Say for what is the average height, what is the variance, how dispersed the height is. If there are more extreme values like outliers, yeah. Okay, yeah, measure of central location. We can use sample mean, sample median, and a measure of the dispersion, how spread or the degree of the spread. We can use variance or standard deviation, or you can use a range, which is a maximum minus the minimum height. We can use interquartile range, IQR. Okay, we have sample 1, 3, 6, 10, 12, 14, 15. So we can find the mean value, we can find the median value. So 1, 2, 3, 4, 5, 6, 7. There are 7 samples here. So the one in the middle, if it's an odd number of sample size, then the middle one will serve as a median. So 10 is a median. Then average will be plus all of them divided by 7. Oh, it is shown here. So mean is 8.71. So that's a mean value. Then the median value is the one in the middle, 10. So then we're looking at the skewness, whether it is right skew, left skew, or the no skew, asymmetrically distributed. Okay. Then next we'll talk about the percentile, quantile, and quartile. Okay, percentile is from 1, 0 to the 100th. Then the quantile is from 0 to 1. Okay, so it is a percentile divided by 100. You convert percentile to quantile. And for the quartile is from 0, first quartile, second quartile, third quartile, to the fourth quartile. So first quartile is equivalent to 25 percentile or 0.25 quantile. Then the second quartile, also called the median, is the 50 percentile and 0.5 quantile. Okay, and there is a concept called interquartile range, IQR, which is the Q3 value minus the Q1 value. Okay, so these are all statistics. It varies sample to sample. Our applications, and there's a example using the chick weight. Okay, so I'll refer to the video lectures to look at the chick weight. Okay, box plot. So box plot is worth mentioning. So the thick thick horizontal bar is the Q2, is the median. Then the quartile 1, the first quartile is shown on the lower bound of this entire rectangle box. Then the higher bar is the third quartile. Okay, then there is a upper whisker and a lower whisker. Then there is a dotted line to connect upper whisker and the lower whisker. We'll look at how to calculate. Then there are a few two circles. If you observe outside of this upper whisker and lower whisker, they are considered as outliers. So we'll look at how to calculate them. It's here, upper whisker, lower whisker. And there is a conceptual two line called upper inner fence and the lower inner fence. We're looking at how to calculate these two upper and lower inner fence as well. So in general, for a sample of numeric values, then generally we can have a few called summary statistics, which is minimum value, maximum value, median, mean, first quartile, and third quartile. So 1, 2, 3, 4, 5, 6. So these are 6-point summary statistics in general. Okay. So based on these 6, we can draw a box plot. So next we are seeing that how to draw this box plot. First, you can find them median, Q3 and Q1. Okay, then next is to calculate the interquartile range. So interquartile range is Q3 minus Q1. So this is all the numbers shown here are the chick weight. Okay, so in unit of gram. So 163 minus 65.5 gram is 97.5. So interquartile range, we have calculated 97.5 gram for the chick. Then next is we need to determine upper inner fence and lower inner fence. Upper inner fence is Q3 plus Q3 value 163 plus 1.5 times interquartile range. Then you arrive 309 gram. Okay, so upper inner fence at 309 gram, and the lower inner fence is Q1 minus 1.5 IQR. So it is a negative value, minus 80.75. It means negative 80 gram. So in real world, it won't happen. So none of the chick will have a negative weight. So this is extremely low. Okay. So next is we need to compare with the max and the minimum to determine the upper whisker and the lower whisker. Okay. So next we look at the upper whisker and the lower whisker. So we compare the minimum value with the lower inner fence first. Whichever is higher, the lower whisk will converge to there. So if the minimum value is higher than the lower inner fence, then the lower whisker will extend to the minimum only. It won't go down further. It won't reach the lower inner fence. Okay, next you will look at the upper inner fence. Okay, upper inner fence. Upper inner fence is to compare the upper whisker, upper inner fence with the maximum. Okay, upper inner fence is 309, maximum is 331. So there will be some more extreme values beyond the upper inner fence. So if in this case, then the upper whisker will extend till upper inner fence. It will be just as high as upper inner fence, then connect to the box with dotted line. Then any individual sample values, the chick weight higher or heavier than the upper inner fence and the upper whisker will be shown as outlier shown here. So in this sample, we have two chick which are heavier than 309 grams. So they are 318 and 331. So these two are circles, become the circles. So they're outliers. So put them together. This is how we actually draw and interpret the whisker. So the rule here is if you observe any outliers shown in a box plot, then that you know the upper whisker is at the same location of upper inner fence. If you do not see any of the outliers, then the lower whisker is shown position at a minimum value of the sample. Okay. Okay, so that's a chick weight. Okay, so next, yeah, you can break down um, the the box plot by another property. So another property here is a chick diet. So diet 1, 2, 3, 4. So I want to bring you one question. Okay, so there are four different brands of the diet or different brand of the chick food to feed the chicken. Which brand, as the owner of the farm, which brand were you going to buy and use in the future? Okay. Yeah, so your purpose is to choose a fish, a food which will give you a general heavier weight of the chick. Okay, so 3 and 4 will overall give you a heavier. But among 3 and 4, which one will you choose? Which one will you choose? Okay, think about it. Okay, next we'll look at the next central limit theorem. Central limit theorem is a long theory, but not difficult. So central limit theorem, okay. So a random sample x1 to xn follows a IID distribution with a mean of mu and a variance of sigma square or standard deviation sigma. A CLT state that distribution of x bar n. So this is the mean of the sample. So suppose random sample, the mean of each of the sample will become closely normally distribution with mean and variance of population variance sigma squared divided by the sample size n. Sample size. When the sample size n is large, 30. Okay, so yeah, it's a bit abstract, but we're looking at that one in a short while. Okay, so generate samples. Okay, so these are a few samples. You refer to the slide. Okay, refer to the video lecture. Okay, so next is I'm going to give you a explanation of central limit theorem. So assume for this cohort of students who are taking AB1202, the big N is 679. So there are 679 students in this cohort taking the AB1202. So big N stands for the population size. Okay, population size. So we want to find a mu value. Okay, mu is unknown. So at the meantime, we are drawing a population distribution. Okay, so it is from x-axis, the random variable is the height of the individuals. So from 150, 155 till 185, 190, and 200 centimeter. Okay, so there are individuals here. So we measure every person's height, then every individual student will have a place in this x-axis. Then we stack them together. Then we derive a distribution of the population. Okay, so assume this is the population distribution, and we do not exactly know what is the average height of the entire cohort. Okay, now next I'm going to tell you. Okay, the Q1, the first quartile value is 166 centimeter. I tell you, and the Q3 is 174, and the medium is 170 centimeter. Okay, next is I want you to draw the box plot, basically determine the lower inner fence, lower whisker, upper inner fence, upper whisker. Oh, I also mentioned there's two person, which is very tall in our class, 191 centimeter and 199 centimeter. Okay, next, how to calculate this box plot, how to draw. So first, calculate interquantile range, which is interquantile range is Q3 minus Q1. So 174 minus 166. Then you arrive 8 centimeter. Okay, 8 centimeter. Then next is your upper inner fence is your Q3 plus 1.5 interquantile range, right? Q3 is 174. So I have 174 plus, yeah, plus 12 centimeter, right? 1.5 times 8 centimeter is 12 centimeter. So plus 12, you get 186. centimeter, and the lower inner fence you are 154. Okay, so next is we want to check the upper whisker and the lower whisker. How do you determine where the upper whisker? You compare the upper inner fence with the maximum height. So we have 199, 199. So which one is higher? You'll find that there are some individual who is actually taller than the upper inner fence. So you know they can be considered as outlier. So when there is outlier, then your upper whisker will be at the same place of the upper inner fence. So your upper whisker converge with the upper inner fence at the same place. Then you check how many people, individual student who are taller than your upper whisker. Then you find there's two. Okay, there's two. So you have two outliers here. Then next you will look at the lower inner fence. Lower inner fence is 154. Okay, 154 is here. 154 is here. So who is the tallest? Okay, who is the shortest? So let's assume the shortest person is lower whisker 159. Actually, I told you there's one person in our cohort. The shortest student is 159 centimeter. So your lower whisker will be at the place of the shortest or the minimum value of this random variable height. Okay, so we're good at the moment. We know how to draw a box plot based on sample, based on the sample. Next is we explain the central limit theorem. So n sample size equal to 3. Okay, 3. What we'll do is we are collecting a few samples. Again, a few samples. We randomly select 3 students from the population of 6, 7, 9 in this cohort randomly. Okay. I have student 1, student 2, and student 3. So these 3 students' height form sample 1. Okay. Then I can move these 3 students back to the population, and I'm going to randomly draw again for sample 2, another 3 students. So this is called sampling with distribution. So for central limit theorem, so you need to draw with replacement. So that means when you put the 3 students back to the cohort, any of these 3 students is still having the chance to be selected in other samples. So this is required because the IID requirement. So if you remove these 3 students, then the remaining cohort, the distribution is actually different from your expected population that you want to study, because you have excluded 3, so this is not fair. So you need to move these 3 back. Every time you draw a sample, the population remains the same. Okay, there are nobody missing there or excluded. So sample 2, you draw another 3 student. Sample 3, another student. Then assume for practical reasons, we repeat for 1,000 times. So there is a k equal to 1,000. So you have k samples. Okay, that's very important. You have 1,000 samples. Each sample contains 3 students and the 3 students corresponding height. Okay. So since you have the 3 height in sample 1, you can calculate the average height of the 3 students of sample 1. So we write it as x bar 1, x bar 1. Okay, so for sample 1, so assume the mean value is 176 centimeter, just for illustration. Then we repeat this one several times. We can calculate the average height for each of the 1,000 samples. So now the x bar, how many x bar do we have? We have k x bar is 1,000 x bar. Okay, so each x bar is an average of n equal to 3 students' height. Okay, so n is called the sample size. Okay, n is called the sample size. K is called the number of samples. Okay, so K is number of samples. So there are different concepts. So this is a usual confusion where the confusion come from. So always, if you feel confused, always refer to this graph, okay? The sample size and the number of samples, okay? So now you have 1000 K, you have 1000 average heights, okay? So they can be slightly different. Then after that, so for this 1000 sample means, okay, average height, we can put them into a new distribution. We can construct a new distribution called height, average height. Though this distribution x-axis is the average height. Okay, average height overall, the scale, the range will be similar to your population. Yeah, it will be similar to your population. And usually it can be narrow. So we'll look at that later. So you stack all those sample means in this distribution. Then there will be a shape. So the shape will be normally distributed if the n sample size is greater than 30. So at the meantime, it's 3. I'll just for illustration, that's 3. So now next is we can calculate the mean value of so many sample means, right? So we can calculate only one single mean value of so many sample mean, 1000 sample means. Assume it is 171. Then n equal to 3. Then we can also calculate the variance of so many sample means. We can also calculate standard deviation of so many sample means. Okay, right. Okay, now next is central limit theorem. So if n, instead of every time we select 3 students, now we select 30 students. So sample 1 contains 30 students height, and the x bar 1 is average of 30 students. Okay, then we repeat it again for 1000 times. So we have 1000 mean value. So mean height. So now next is when sample size equal to 30, I want to ask you how many student has been actually selected. How many students have been actually selected? You can find for sample 1, 30, sample 2, 30, sample 3, 30. So 30 times 1000. So it is 30,000 students has been selected. Okay. Then how many average height or sample mean that you have is 1, 2, 3, 4 K sample means. Okay, K sample means. Then from here, how many X bars will you have in the sampling distribution of the mean? So this distribution is a sampling distribution of the mean. How many X bar you have? You will have K number of X bars, so 1000 X bars, okay? So now, since the sample size is relatively large, 30 and above, then according to CLT, central limit theorem, the distribution of this sampling distribution of the mean, this distribution will be a normal distribution. Okay, so this is the theory. So this will be a normal distribution. Okay. And for this sampling distribution, it has a mean value. We will expect the mean value will be same as the mu here, the population mean. So this is the consequence of CLT, and at the same time, the sampling distribution's variance, which is S squared, will be equal to the population variance divided by n, which is the sample size. Okay, so that will be the expected result. Okay, so now hope you are okay at the moment and be very clear on this matrix. Okay, k number of samples. For each sample, how many individuals are being drawn? That is the sample size, okay? So next is we are going to look at a few of the simulations. So I'm going to run it. I'm going to do some demos for you. So create one samples, draw a samples from a uniform distribution. So R uniform, get a random number from a uniform distribution. Okay. So we draw five digits, five numbers from a uniform distribution, 1, comma 2. So minimum 1, maximum 2, I will get 5. So we can find these are the 1, 2, 3, 4, 5 numbers and what is the mean value. Okay, so we can do that. Next is we are going to plot this value. Okay, we plot this. 1, 2, 3, 4, 5. These are the 5 samples that we draw from a uniform distribution, and what is the average value x bar of these 5. Okay, and this is the first sample. Okay, so we are going to calculate the mean for the next 6 samples. 1, 2, 3, 4, 5, 6. Okay, so now let's plot it. Let's show it. Okay, these are the 6. Okay, let's have a look. Sample 1, 2, 3 till 6. Okay, each of the sample contains 5 individuals. Okay, so what is the sample size here? N equal to 5. No? 1, 2, 3, 4, 5. What is the k value? How many samples do you have? You have k equal to 6. Okay, so in this example, we have n equal to 5, k equal to 6. Okay. Next, visualize the sampling distribution. Okay, so now we calculate the sample mean equal to the mean value of these 5. So, okay, so we can calculate the sample mean. So we run this sample mean. We'll have a look what is sample mean. This is the sample means. Okay. Then the actual sample means we can find what is the mean value of these 6 mean value, which is around here, right? Around 1.5724. Right? The theoretical ones is the actual mean that from these 6 samples through the simulation. The simulated mean of these sample means are 1.572. So the theoretical one is the uniform distribution 1 to 2. The theoretical mean, population mean is 1.5. Okay, right. So these are the actual mean and these are the theoretical mean. Okay, so let's have a look. So we have 6 sample means. 1, 2, 3, 4, 5, 6. 6 sample means. Then for these 6 sample means that we randomly draw, the simulated actual mean of these 6 samples are 1.57, and we know that the theoretical one is 1.5. So this is actually showing you that the sample mean of the sampling distribution, this is sampling distribution of 6 samples, and the sample size is 5. Okay, so the actual mean of this simulation is very similar, very close to the theoretical mean. So overall, it shows you that the samples limit, the central limit theorem is working. Okay, so we the remaining sum of the code is for your exercise. Then you can run and understand by yourself. Then I'll show you next is the demo part, more demos. Okay, there is a few skewness. Okay, common zero of skewness. Okay, let's have a look at the skewness. Distribution and mean. Distribution and plot of sample 2. Mean and median plot of sample 3. Okay, some of them. Okay, so here is showing you right skew, left skew, and their corresponding box plot. So I'm going to display to you. Okay. So again, this is a simulated data, okay? So this is showing you for the left skewed distribution, your mean value will generally be lower than the median value. So for the symmetric ones, you are seeing the mean and the median value are very close. For the right skewed, you are seeing the mean value are generally higher than the median value for the right skewed, okay? And the below three are the corresponding box plots. For the left skews, you are going to observe more extreme values to the left. Okay, so there will be more likely to have a more likelihood of extreme outliers in the left side. So the left side is the lower whisker. Okay, the higher the value is the upper whisker. Then for the symmetrically distributed, you are going to observe overall similar number of outliers beyond the two whiskers. Then for the right skews, it's less likely to observe extreme values or outliers to the left, but there will be more on the right tail or right tail side. Okay, so this is the key takeaway for you. Minimum, maximum. Okay, so this is summary. So exercise, the common statistic in R application, calculate descriptive analysis, week 6.3 common statistic. So here is we're looking at the chick weight. So weight, time, chick, weight, time is the days. Chick one died, one without the diet the chick is having. So here is a histogram of the chick weight, the chick weight. So first, my question to you is, this is a distribution of the chick weight. Is it normally distributed? No, it is not normally distributed, right? So this shape is obvious, not symmetric. So is it right skewed or left skewed? So from this histogram, you can see this distribution is a right skew. So it has a longer tail to the right, so it's right skew. So mean value and median value, we'll see that mean value is higher than median value in general. This is right skewed. So what is the variance? What is the standard deviation? 71 gram. What is the range? Okay, what is the range? Returns a minimum and a maximum. Minimum 35 gram, maximum 700 or 373 gram. Then we'll give you a 6 point summary. 1, 2, 3, 4, 5, 6. Based on this, you can draw a box plot. So quantile value, okay, quantile value, yeah, 0 to 100 percentile. So quantile function will give you the percentile. Okay, then medium. Okay, then Q1, then quantile 75 percentile, then interquantile range is 100.75 gram. Okay, next is measure of association. Okay, so these are the measure of association. Then there's a heat map. So, okay, this is which one is which one. This is the example. So our application with whiskers. Okay, so let's have a look at the whiskers. Whiskers. So Q1 is known to you, Q3 is known to you, minimum is known to you, maximum is known to you based on the summary. Then calculate the interquantile range. So let's have a look. Interquantile range. This is interquantile range 97. Lower interference, then upper interference. Upper interference. Yes, right, 309. Calculate the lower interference, where the lower whisker. So run it to compare with the minimum value and the lower interference, whichever is higher, then that will be the lower whisker. For upper whisker, so use a minimum, whichever is smaller, whether it's maximum value, or the upper interference, whichever is lower, it will be the upper whisker. Then after that, we can show it. Okay, so these are the few values. Then next is to find the largest 6 data values. Largest 6, then you see how many are larger than 309 point on the upper whisker. How many are greater than 309.25? There will be the outliers. So there is 2 here. So finally, let's plot it. Okay, let's show it. Let's show it. So I'm adding a few lines for you. Okay. So this is the box plot for chick weight diet equal to 2, okay, equal to 2. Then this is the R implementation and the visualization for the example that we have seen in the slide. Okay, good. Next is okay, subplots by groups, so we can break by diet. Okay, so break by diet. Oh, a few more is a violin plot. So basically, it's a box plot combined with a distribution. Combined with the distribution. So you can not only see the box plot, but you can see the distribution as well. So it is also clearly show this is right skew. So you turn your head 90 degree then. Here is the left side, here is right side. Okay, right tail, right skew. Then exercise, we will skip exercise. Okay, then next is the central limit theorem, Golden box simulation. So I just run a code for you to visualize the Golden box. Golden box. Okay, for Golden box, what kind of distribution is this? So some of you may say, this is normal distribution. Think twice. This is not a normal distribution. We must have covered the PDF and PMF and CDF. So which function is this? Is it CDF? No, it's not CDF. Is it PMF or PDF? How do you determine whether it's PMF or PDF? You need to determine whether the random variable is a discrete random variable or continuous random variable, right? So for a normal distribution, the random variable is a continuous random variable. Then you look at these Golden box. So when there's a lot of metal balls go down left, right, when they hit the pin, left, right, left, right. How many possible outcomes are there? First, what is the sample space? Number of sample space. The sample space from -12 to +12, right? Then it is a discrete. So if it's a discrete random variable, it will not be a normal distribution. So it is a discrete probability mass function. So in fact, this is uh, it is a binomial distribution, 12 layers. So for the first layer, if you drop one metal ball, and hit the first pin, one layer, it will go left or right, right? So there's two outcomes, left or right. So it is similar to toss a coin, head and the tail. So if you toss a coin once, what is that distribution? It is the Bernoulli distribution. It's a Bernoulli distribution. Then if you repeat the Bernoulli experiment again, then it becomes a binomial. So this is actually a binomial distribution. It looks normally distributed. But later in the tutorial, you are seeing that we can use normal distribution to approximate a binomial distribution. Okay, so we'll look at that later. Okay, so next is visualize the central limit theorem and the effect of sample size n and the size of sample list k, or the number of samples k. Okay, so we set a seed for reproductivity. Then next is we're constructing a population. Okay, the population is a uniform distribution. Okay, it's a uniform distribution. So we have a large number of individuals that are being drawn from a uniform distribution to serve the purpose at the population. So it's 500K, 500,000. So let's run it. So we have a population here now. Let me clear everything here. Yes, let me start with this again. Okay. We have a population of 50,000 numbers. So we have a lot of numbers here. Okay. Then we can see the maximum, minimum, the size, and the variance, okay, of this population. Next is we are drawing this. So this is the population that we created from about 10 to 30. The mean value is about 20. Okay, so 20. Then the variance is 30. So just remember these few numbers, minimum 10, maximum 30, then mean value is 20, then variance is 30. So around that, okay. So next is we are going to draw sample size. Okay, sample size. Okay, we have sample size. Sample size of 3, 30, 300, 3,000 sample size, and number of samples, which is k value. It can be 10, 100, 1,000, and 10,000. Okay, next you are going to build a chart. Okay, so uh, don't worry. So first, look at this. This is the population. Okay, so this is a population. It's a simple uniform distribution. Mean value of 20, variance is 30. Okay, so next we look at this chart. Let's explain this chart to you. First, let's look at the first column. Okay, let's look at the first column, the four figures. What are the four figures? Four charts. The four charts are n equal to 3, sample size equal to 3, 3, 3, 3, 3, or sample size equal to 3. Okay. Then the mean value, you are seeing that all similar to 20. Okay, similar to 20. Then the difference is the k value, the number of samples. So here you have 10 sample means. In the second chart, you have 100 sample means, 1,000 sample mean, and 10,000 sample mean. So the k value increase from top to bottom, okay? But the sample size remain the same. So you are seeing that, yeah, the more of the samples, the more smooth the distribution is. Then you also observe the mean value are all the same, similar, around 20. So yeah, it's good estimate. So the mean of the sampling distribution is a good estimate of the population's mean. This is the first takeaway. Then second is look at the variance. So the variance is around 10, okay? So 9.9, 10, 11, 12, that's around 10, okay? So this also tells us the variance of the sampling distribution is calculated theoretically by the population variance. Do recall 30 divided by the sample size n. 30 divided by 3, n equal to 3, is around 10. Okay, so this is the central limit theorem in effect. Okay, so your variance of your population 30 means 20. So for your sampling distribution, the mean value will be same as the population mean, and your variance of your sampling distribution is the population variance divided by n. Okay, so around 10. So now next, let's look at the last row. Okay, last row, k all equal to 10,000. So k are equal to 10,000. The difference is the n increase from 3 to 30 to 300 to 3,000. So the sample size increase. Okay, so when the sample size increase, what we have observed, the mean value of these four, the bottom four, remain the same, around 20. So the sample mean is a good estimation of the population mean. Okay, then the variance you'll notice it start to change as well. So for the first one is 10, which is 30 divided by 3. Second one is around 1. It is 30 divided by 30. Then 30 divided by 300 around 0.1. Then 30 divided by 3,000 is 0.01. Okay, so you are noticing that the variance gets smaller and smaller for the sampling distribution when the sample size increase. Okay, so again, this is the central limit theorem at play. So now from the left side to the right side, we're seeing the distribution, the sampling distribution gets slimmer and slimmer clustered together, slimmer and slimmer, slimmer and slimmer. Okay, so when it gets slimmer and slimmer, you are noticing that the majority of the sample mean is around a specific number, 20. So majority of the sample mean is actually very near to 20. So when it's very near to 20, we can actually say we are more confident that the sample mean, the mean value of the sampling distribution is a very good estimate of the population mean value. And with it, very strong confidence because all the sample means are just very near to 20. So we're very confident. Compared with the first one, when sample size is small, then you are noticing some of the sample means are actually varies quite a lot from even 10, 15 to 25, 30. So each of the sample mean, in fact, is a legitimate and trustworthy estimation of the population mean because all of the sample mean here, how many sample mean do we have? Again, the data points in the sampling distribution are all sample mean. The sample mean, we have 10,000 sample means. So each one of these 10,000 sample mean should be treated fairly and equally to have the same chance to be the same as the population mean. Okay, so because each of the sample mean that we draw, each of the sample we draw are aligned to the IID condition. So we can't say sample one is more trustworthy than sample two, or sample two is more trustworthy than sample three. All these 10,000 samples, they are equally trustworthy. Okay, that's very important. Okay. Okay, so that's that part. Okay. Next is I show you a different population distribution. So don't worry. This is a called chi-squared distribution. So what I'm trying to show you is this distribution is obviously not symmetric. Is it obvious not a normal distribution? And earlier the uniform distribution is also not a normal distribution. So this is not a normal distribution and it has a right skew shape. Remember the mean, 5. Mean is about 5, then variance is 10, okay, for this population. Mean 5, variance 10. Then we repeat the same thing. We draw samples and create this chart, okay? This 16 chart. Again, what do you have observed? We look at this, k equal to 10,000, mean sample size 3. The mean value of this sampling distribution is a good estimation of the population is 5. The variance is 10. The population variance of 10 divided by 3. 10 divided by 3 is 3.33333. So it is aligned to the observation. So the actual variance to the sampling distribution is 3.333, which is the 10 divided by 3. Then you look at this sampling distribution. When the sample size is small, you observe this sampling distribution is slightly right skewed, right? It is not strictly symmetric, right? We're not seeing it symmetric. It is actually right skewed. Then you increase the sample size from 3 to 30. Oh, the second one looks more normally distributed, more symmetric. Then the third one, n equal to 300, it is almost impossible for us to tell whether it is right skewed or left skewed. It is more symmetric. Then when sample size grade gets larger, it's more symmetric. So this is again showing you central limit theorem says that when the sample size is larger, the larger the better. But empirically, if it's greater than 30, it is already very well symmetric. It's a very well distributed, showing the symmetry. Okay, again, another thing you want to think of is the sampling distribution. When the sample size is small, it will still have the shape of this population distribution because population distribution is right skewed. Okay, good. Okay, next is exponential distribution. So again, give you an exponential distribution. This is completely right skewed. Exponential distribution, then what you can observe from the population is the mean is 1, variance is also 1. Okay, for this exponential distribution, mean value 1, variance 1. Okay, the population there, let's look at that. So mean value 1, variance is 1 divided by 3, 0.333 around there. So it is also the right skew, right skew. Then n equal to 30, then yeah, more symmetric, mean value remain the one, remain the same. So the mean value of the sampling distribution is a good estimation of the population mean, and the variance continues to reduce, and the variance of the sampling distribution is the variance of the population divided by the sample size. Okay. So this is about the central limit theorem. So finally, I want you to think of, according to the central limit theorem, it says the sample size must be larger. Great, bigger and better, or at least 30. Then what about the k value, number of samples? According to the central limit theorem, what is the requirement for k value, number of samples? You think of it. If you recall the definition, the central limit theorem did not ever mention the k value. It was not mentioned. Okay, that's why I want to introduce this new concept here so that you won't confuse with the number of samples and the sample size. Okay, so the number of samples k in central limit theorem, it is not mentioned. So in fact, the expected k value to make the central limit theorem to be established is a positive infinite. So you need infinite number of samples to be drawn. Okay, so that's central limit theorem. So central limit theorem only defines the n must be large, while the k is expected to be positive infinite. But from the simulation point of view and practical point of view, we are not able to get k to be infinite. Okay. So for this simulation using R, we get a very large k value, but it cannot go to infinite. Okay, so that's all for these lecture part. Okay, so lecture part, general sample mean distributions. Okay, there'll be a few other things to talk about. Getting a sample. Okay, sample. Okay, so this is sample banana with replacement, without replacement. Okay, let me have a look whether it is worth to mention this. Okay, let's have a look at this. Generate sample mean distributions. Okay, clear these. 6.6. Yeah, here I do a little bit art tutorial. Okay, so sample a list. So okay, you get a list of 1, 3, 5, 7, 9. So this is a list using a function called C function. C function means combine. It's actually combine. So you're creating a list of 5 numbers. Then you use sample function. So sample give the list. Then I want 3 of them. So just sample 3 of them. So by default, this is sample without replacement. So you get 3 values from this list. Okay. So you get 1 first, then you do not put that person back. Do not put that individual back. Say you get 5 first. After you get 5, so you remove 5 from the list. What's remain is 1, 3, 7, 9. Then you get another value. They get 1, then you remove 1 from the list. So this is default behavior of sample without replacement. So sample 1 to 10. 1 to 10 will give you 10 numbers from 1 to 10 integer. Then we sample 10. So what are we doing here? We are doing give me a random sequence of these 10 numbers because there are 10 numbers and I want to get 10 out of them. So basically it's give me a random sequence of 1 to 10. Okay, sample function, randomly draw. Okay, you can say apple, banana, coconut, durian. Give me any of these 2 that you can sample many times. Then next is I have this list, give me 5. You give it arrow. Why? It's because you have only four elements, then you want to get 5, then it's impossible. But if you're adding a replace, then it becomes possible. So each time you get one fruit out, then you put it back. We get one fruit out, then put it back. And with replacement, so we get 2. So there is a chance to get a duplicate. So let's say I get 6 out of these. Then they give me 6. So you're observing there will be duplicates. Apple appear a few times, right? Multiple times. Coconut also appear 2 times because of the replacement. So after we get one sample out, then we'll put that sample back into the list. Then assign 250 students to unique seat. No student is allowed to sit on another student's lap. Okay, so this is assignment 200 student to a unique seat number. Okay, so unique seat number will have 500 seats. 500 seats, you get 250. Fair die sampling. Okay, sample 1 to 6, then 10 times. Sample 6, 10 times. 1, 2, 3, 4, 5, 6. Fair die. Roll it 10 times. Then replace true probability. So this is unfair dice or loaded dice. Now, digit 6 has a high chance, 50% of a chance. Right? You can assign the probability to it. So in order for you to find the sample function, you can write this random sample and permutation. So if you type a question mark and the function name, then it will show you the documentation of that function. So sample X, size, replace, and probability. Okay. So these are and you could scroll down to look at some of the examples. For examples, 100 Bernoulli trials. So 100 Bernoulli trials. Type here, okay, 010101, Bernoulli, you can say this C is head. You can say head, then here you say tail. 100 times, okay, you flip the coin 100 times. So it gives you random outcomes of flipping the coin 100 times, okay. Okay, very good. Next is we're looking at the tutorial. Okay, finally we're moving to tutorials. So random sampling requires the ID condition, independence, identical distribution of the sample points. Suppose I plan to conduct a study about the GPA of the current NTU student, blah, blah, blah. Though the first one refer to the reference solution, and with some help of AI, you can have a solid idea. Then we'll move on to question 2. Seatbelt contains the monthly road casualty in Great Britain. From this one, use help seatbelt and view seatbelt to see more detail about this data set. Note that the chicken weight we saw, now we can use something. Then seatbelt is a time series, then you have some problem. Now you need to use another method. So, okay, what are the sample means and medium of the drivers, kill a series, and okay, so let's look at that. So now open this R solution that you can find from the seminar specific content. Okay, tutorial 6, question 1. Okay, refer to question 2. ION. You can type help seatbelt. So what is the seatbelt? It is the UK driver deaths in the time series. Okay, so you have a few of them, view the van killed and so on. Okay, so next we have a look at the last 1536 line of records. View, you view it. Driver killed. How many drivers? Front, rear, front, rear, KMS, patrol police, van killed, and so on. Whether the law has been implemented or not implemented. The length of it is 192. Okay, 192. 192 lines. 192 lines. Okay, next is to obtain the sample mean and the medium of driver, we use this. Okay, so we need to find the seatbelt. I'll try these seat belts. We assign to a data seat belts. Okay, we just have a look. It's called time series. Okay, it's a time series. You can type a structure, STR structure, to have a look at the seatbelts. It is a time serial 192 observations and 8 columns from this year to this year. Okay. So next is remember we earlier we actually used this function in earlier weeks. We're saying that to the left of this comma is a condition. To the right of the comma, it is the column name that you want to include. So this is the column name. So yeah, drivers column names. So how many number of drivers for each year, each month, each year, each month. So that's the drivers, okay? So now we want to find the mean value of it. So how many mean value? So 2.1. What the sample mean and the median of drivers killed or seriously injured. So that's driver one. Drivers is a number of drivers seriously injured or killed. So for each year, it is here. Then find 1670.307. Then median. What is the median? Median is 1631. Okay. Then next is okay. Show and filter the drivers above average driver. Okay, so median 163 1631. Okay, so this driver is greater than this. So to the left of it. So this is a condition, right? So this is a condition. If we add a condition to it, so if we do not add any condition, we have this. Without condition, we have this. This is all the total drivers. So now I need to add a condition. So what is a condition? Condition is this. This one is greater than 1631. So they will tell you for each of the year whether it's true or false, true or false, true or false for so many numbers. So we add this field into the left of the comma. So this is a condition. So we run it. Then they show you only those driver, the years whose driver killed are higher than 1631. Okay, so this is for illustration. Now, then next you can have a look at the histogram of these drivers being killed. So this looks like a normal distribution, but not actually normal. I think it's right skewed, a little bit right skewed. There's more extreme car accident that more drivers are being killed. So this right skewed means number of drivers being killed a particular year. If it's right skewed, so on the right side or right tail, there will be lesser data. There's a longer tail, flat one, but there's more extreme. So yeah, so this is telling you based on the distribution, you can interpret what's happening. Did the sample mean and median increase or decrease after the law of compulsory wearing seatbelt was introduced? Check the law variable. Okay, so there is a law variable. The law variable shows 0 and 1. 0 means that year the compulsory seatbelt was not introduced. Then some of them are EY. Then want to compare whether the deaths are dramatically reduced. Okay, seatbelt law equal to 0, equal to 0. You are seeing some years are true, some years are false. True means 0 means the seatbelt has not been introduced. Okay, 0 means not introduced, 1 means introduced. Then we're seeing that for each year, what are those number of drivers, the years whose drivers are killed before the law implemented. So before that, the mean is 1717, median is 1653. Then after regulation, then it is dramatically reduced. You can see it is actually dramatically reduced. Okay. from 1717 to 1321. So the difference is big. So calculate the sample mean and the standard deviation of drivers plus front. Drivers plus front. Okay. Mean value. So let's have a look at the mean value of drivers plus front. This is a drivers mean value. This is the front for each year. You add them together. Okay, you add them together. Yeah, add them together. Then find the mean value. So which is this one. So 2507.526. Then if you add the mean value of driver, then add the mean value of the seat belt, they give you the same result. Okay, give you the same result. 2507. Okay, we have calculated that one. Then variance and standard deviation. Okay, so next is that we're showing you the variance. Driver front, which is a driver plus front. Okay, plus them together. You show the variance of it. You show the standard deviation of it. Okay. Then next is variance driver front. Variance of driver plus variance of seat belt plus 2 covariance drivers and a seat belt. Okay. It gives you variance from 196,524. Okay, they give you the same one, then give you a square root, you also get the same one. So this is actually showing you earlier a few weeks ago, we have learned bivariate distribution and variance calculation of two random variables, right? So the first method is the organic method. So first we sum this driver and from together, we get two variable combined to one variable. Then after that, we calculate the variance. So they will give you the correct answer. Then, but if you want to treat these two random variables as two separate ones and calculate the variance of those separate random variables, then you need to add the 2AB, if you remember, 2AB times the covariance, right? So variance bracket x plus y inside it equal to the variance of x plus variance of y plus 2AB. Which is the coefficient of x and y, which in this example is 1. 2 times 1 times 1 times covariance of x and y. Okay, so that's showing you the effect of two random variables. Manual calculation using mean value drivers. Okay, so this part is the population variance. So if you are using the variance function and standard deviation, it is calculating the sample variance. If you treat it as a population, you calculate it manually using the standard formula, which is each individual random variables minus the average of the random variable squared divided by the n size of this population. If you treat it in this way, you'll find that the variance is 1.55, which is 1.5506. Okay, 1.5506, which is smaller than 19652, which is smaller. Then your standard deviation of the population is also smaller. So if you treat it as sample variance, the variance and the standard deviation will be larger than the population variance and distribution, variance and standard deviation. Okay, so this is the part. Okay, then we're moving to next, right? The next question to consider following 5-point summary. 5.1, 2, 3, 4, 5. Instead of 6 point, it's 5 point. It has no median, have no mean. obtained from data set with 200. Calculate the Q1 and Q3. Okay, Q1 and Q3. Q1 is here, 54. Q3 is uh, 78. Calculate interquartile range. 78 minus 54. Suppose we want to construct box plot based on the information, determine the value of lower and upper whisker, any outlier exists, okay? Upper and lower whisker. So based on these, Q1 is 25 of the observations are less than 54, okay? So, okay, then 75 quartile, 75 percentile is the third quartile. Then 78, it is a mean value is 150 to 151 sample point because we have 200 sample points on an even number. Then interquartile range is 78 minus 54 is 24. Okay, so low interference is 54, Q1 minus 1.5, interquartile range is 18. 18 is smaller than the minimum. Okay, 18 is smaller than the minimum. Then the lower lower interference is 18. So lower whisker is 34. Okay, whichever is larger. Then upper interference is 114. 114 is greater than max. So your upper whisker will be the max value. Okay, whichever is smaller. Upper whisker is the minimum of upper interference, comma max. Okay, so max is smaller, so upper interference is at 98. So no outlier. Okay, no outlier. No outlier. Because the two lower and upper interference incorporate the minimum and the maximum. So no data points exceed these two fences. So there's no outliers. Question 4. Question 4. Okay. The R command such as R by R norm generates samples from underlying distribution for R by norm, then okay, 250.5 generate two samples from a binomial distribution that involve 5 trials. And a success of the probability of 0.5. The command, in fact, computer robots prescribes all these. Okay, set the seed of it, then random. But now you want to run these after set seed. Please do it without setting the set. You draw 3 values from standard normal distribution. The distribution and another 3 values from the uniform between 0 and 1. Compare result with others. Okay. 4.1 R norm n equal to 3. Okay, I think one thing is you should learn first is R norm. R norm. So normal distribution. So you have D norm, P norm, Q norm, R norm. Okay, D norm is density function. P norm is the CDF, cumulative distribution function. D norm is the PMF or PDF. R norm is get a random number from a normal distribution. Q norm is to get the quantile value or the Z value based on the probability. While P norm is to get the Z value based on the quantile. Sorry, P norm is get the probability based on the quantile or Z score. Then Q norm is the inverse function. Get the Z score based on the probability. So R norm. Okay, R norm. How do you use R norm? R norm is says n mean and standard deviation. For me, I have a habit that I always want to type the coefficient so that you know what exactly it is. Now, n equal to 3, that means I want the 3 samples, okay? And the mean is 0, standard deviation is 1. So this is a standard norm distribution. This is standard norm distribution. Then we run. So get 3 numbers. If you run it again, you get another 3 numbers. You get again another 3 numbers. Again another 3 numbers. Then next is R uniform. Again, you can have a look at R uniform. are uniform. Are uniform. Okay. Okay, if it's a function, you are not necessary. When typing the helper function, you are not. It's not always required to type the the parentheses. So Arnold, minimum value, maximum number value, and the number of samples. Okay, 3. Minimum 0, maximum 1. So run again, you are seeing that each time you get different numbers. Okay, so Q4.2 is saying now set the seed to 50 and repeat above, compare your result with others. So set seed 100, R norm 3, R uniform 3, you get these 6 numbers. Then you run the set seed again, and you run this code line of code, you observe that these 6 numbers are the same. So set seed is to set a long list of random numbers. Then the R function, R norm, will consume the first 3 random numbers from the first three fixed random numbers from this long list. Then use that 3 random numbers to generate 3 samples from a standard norm. Then next is R uniform is going to consume the following 3 distinct random numbers from the long list. So R norm will consume the first 3, then R uniform will consume the 4th, 5th, and 6th random number. Yeah, so in total, there are 6 random numbers being consumed. Okay. Then if you have any other line of code command which involves randomness, then it will start to consume the following random numbers from the long list of random number priorly generated based on the seed number 100. So 100 will seed number 100 will give you a unique list of very long random numbers. Then if you change to 99, 99, then it give you another different very long random list. So your result will also change. Yeah, I don't know. But as long as you use the same C number, and you repeat again, you are observing that the results, the samples being generated are the same. Okay. So for loop, okay, for loop, let us to repeat the loop. Use a for loop to calculate the sum of the first 100 squares. Okay, then set the seed to 100, do the same again, and where x follows uniform 0 to I. Okay. So think of x as a piggy bank that you want to keep adding values into it. I power 2 for 100 times. Okay. So for loop. X start from 0. For I in 1 to 100, so we are going to repeat 1 to 100 times. Then each time x equal to x plus x power 2. So this reads let x equal to the current value of x plus I power 2. Okay, so I value changed from 1 to 2 to 3 to 4. Let's run it. So now you are seeing that after running the for loop, so cat command is to show the display. Okay, cat, you can put some literal here, index here. Seeing index number x value is the actual x value. X when I equal to 1, x initially is 0. The x equal to 0 plus 1 power 2. So 0 plus 1 is 1. Then use 1 to assign to x. Then x value changes. Then the first run is x equal to 1. Then the second one is when x is now 1. So you put 1 plus now I is 2. 2 power 2 is 4. So 1 plus 4 is 5. So x equal to 5. And so on. So this is 1. 1 square, 2 square, 3 square, 4 square. Yeah, so okay, so this is x contain all those lists. Okay, so we can do this. Then x yes. So finally, x equal to this value. Okay, so there's another implementation here is x, let's create again, initialize as a 0 or a list of 0. Then for I in 1 to 100, so xi, x1 equals to 1 powered 2, x2 equals to 1 powered 2 powered 2. So in this example, then we're showing you x1 is 1, x2 is 4, x3 is 9. So you have a long list. So x is 1, x1 to x100, okay? Then there's a 100 number. Then after that, you sum them together, you can say, hey, we arrived at the same value. So there's a few ways for you to implement it, okay? For this course, there's a few other ways. Let's say x equal to c to 100. So that's a trick. Okay, so let's have a look at x. X is just 1, 2, 3, 4 till 100. So you use one column. 100, you can create a list of 100. Then after that, you do an x power. You just have a look at x power 2. What is the value? X power 2. So each element from this list will be applied for a power of 2. Then if you sum them together, then we say y equal to this. So you have a y value. So then y equal to this, then y is this long list, then you sum of y, then you get 338350 as well. So there are a few ways to implement it. Then 5.2, what is 5.2? 5.2 set the seed to 100 prior to the loop, generate the value of x1, 2, 3, 4, 5. Then x again, xi follows uniform 0 to I. So x, when I equal to 1, the uniform 0 to 1. I equal to 2, when x to 2, and generate x2, then it's uniform 0 to 2. Okay. So until I equal to 100, x uniform 0 to I 100. Okay. So let's first I equal to 1 run uniform n5 maximum minimum 0 maximum I. So you run it again, you give a few numbers. So I equal to 10, you get 5. Then you are seeing some values are increasing. So I equal to 100, you draw 5 numbers from minimum 0, maximum 100. So you get 5 values. Okay. So now we are going to create a list called x equal to a list and set seed 100 for I in I 100. So xi again, we are storing 100 random numbers to the x1, x2, x3 until x100. So for xi, I need to draw only n equal to 1. I draw one value. Then the minimum is 0, maximum is the current I value. Okay, then we display it. So set seed for loop. Okay, so you can have a look. For x equal to 1, you draw from 0 to 1, uniform 0 to 1, 2, 0 to 2, 3, 0 to 3, 4, 0 to 4. Okay, so you are seeing that the random number is able to be higher and higher. Depends on the I value at the moment. So if I value, let's say I value 65, at that moment you do a random drawing, they give you 28. So yeah, when you have last few, then they give you the range of uniform 0 to 100. Okay. Then after that, you sum them together. You get 62641. Something like that. Then if you follow the same, you use the same seed, everyone using the R should get the same result. Okay, so same result. So this makes your answer to the quiz questions standardized. So we are going to set one standard answer. Then we will advise you with a C number. So during your quiz or test, then you will need to key in a seed number. Then after the C number keying, your result will be a fixed number. Then the anti-Euler system can use automatic markings to check to evaluate your answer. Okay. So question 6. The graduation rate of a training program is estimated to be 30%. The program admits 10 trainees per month. Then you need to really understand the problem. Suppose admission only keeps data from the recent 3 months. If we were to use the data to calculate the average number of graduates per month, first thing, what distribution would be appropriate? So it is a binomial distribution because each trainee either fail or not fail, because you have 10 trainees. So out of these 10 trainees, each of them either fail or pass, and the graduation rate is 0.3. So on average, out of these 10%, 3 are expected to pass every month. So it will be around 3, sometimes 0, sometimes 1, 2, 3, 4, 5, 6. Maximum can go is 10. There is a chance to get 10 out of 10 pass, but the expected value, the expected graduates per month is 0.3 times 10. It is 3%. So it'll be around 3%. Okay. So if you sample 3 months, you will get 3 digits, around 3. Okay, then use the follow to generate 1,000 sample mean observations. Okay, sample mean observation. So yeah, sample mean observations. So I'm going to calculate histogram of the distribution, set the C value to 1. Okay. Okay, so we were to use the data to calculate average number of graduates per month based on the 3 values. Okay, based on the 3. Every 3 months we have average. Every 3 months we have average answer. Okay, so instead of 30 months, so 3 instead of 3 months. Okay, let's first binomial and Poisson binomial. So binomial random n sides probability. N sides probability. So let's have a look. Binomial n equal to 3 sides 10 probability 3. So most of 3 recent months, so n equal to 3. So size equal to 10, that means 10 trainees. So we can do these first. Let's try these first. Let's try n equal to 1. N equal to 1, that means I want to get 1 value, and we have 10 trials. Size equal to 10 trainees. Each trainee has a probability of graduate of 0.3 and independent to each other. So trainee Sam has a 30% of pass, trainee Jesse 30% pass, trainee Lily 30%. So they are all individual independent. So now this is month 1, then I want month 2, then month 3, so I got 3, 4, 6, right? So you can test n equal to 3, that means 3 months. I got 3 numbers at the same time. 3 months graduate. The first month is 4, second month is 0, third month is 3. So this is how we interpret it. So next is a number of samples. Or how many? Let's use for loop to generate 1,000 sample mean observations. Okay, we need to generate 1,000 samples. So this is the k value. Okay, in practice, we need to assign a k value, number of samples, or else R cannot handle and we can't actually do the simulation. So that's a k value, number of samples. So now X bar is repeat 0 for k times. So this is just showing you the average of these 1,000 samples. So again, if we run R by norm, n equal to 3, how many samples have we generated? We actually generate only 1 sample with sample size of 3. So these 3 values form sample 1. Then we need to repeat 1,000 times. Then for sample 1, we need to calculate the average of these 3 months graduate. So 261, you add them together, which is the a, I mean, 261 million. No, mean value. Do this. Divided by 3. It is 3. Okay, 3. 261. Great. You need to put it into a list in order to use the mean value, mean function. Okay, so now we have ready. We create set C to 1, then we say from 1 to 1000, then x bar 1 is the mean value of this. Okay, the mean value of this. Let's try mean value. Mean value is only one value. Okay, mean value only one value. Mean value, mean value, mean value, mean value. Okay, so this is the mean value. Okay, okay, okay. Okay, good. Good. So now let's see. Let's see, run it. Okay, then you show the bar. Okay, so these are the 1000 average. Okay, so you see the average is around 3 because the expected value is 3, so it will be around 3. So next is we already have this 1000 mean value. Okay, 1000 k equal to 1000, n equal to 3. So each of the mean value that you see here, each of this 1000 mean value is average of the 3 months graduate number, also n equal to 3. So now next we draw a histogram of it. So I think this is a histogram. Okay, so histogram. It looks quite normally distributed. Then what is the variance? What is the standard deviation? Variance is 0.72, standard deviation 0.84. Okay, now, so 6.1 we have completed. Next, you will look at 6.2. Repeat one, but use 30 months instead of 3 months. Compare the two histogram and identify the main difference. Okay, so this is a histogram of n equal to 3, x bar 3, x bar n equal to 3 months. So now, instead of n equal to 3, we have n equal to 30. Earlier was n equal to 3, size 10 equal to 3. So just have a look. They'll give you 3 values. Okay, n equal to 3 values. Now n equal to 30, they give you 30 values. 30 months, 30 months graduate. Then we are going to simulate 1000 times. Okay, bar 30, repeat k times. Again, we do 1000 simulations, 1000 round of simulations here. 30 instead of 3 would become 30. Okay, so let's have a look. These are the 1000 simulation. Each simulation used 30 months graduate numbers. Okay, so histogram. So this is a histogram of x bar equal to 30. How many data points are there? 1000. Each 1000 is average of 30 graduates. Then here is x bar 3. How many data points are there to form this distribution? K number, 1000 mean values. 1000 mean graduates. Each of the mean here is average of 3 graduates, 3 months graduates. Okay, so the difference between these two is what you're seeing is the second one looks more normally distributed and symmetric than the first one is more loosely. It is 1, 2, 3, 4, 5. There are some extreme values more here, 6. Then while for here is you are seeing it's more centered in the 3, they are more symmetric. Okay. Then the variance and the standard deviation also change. So right. So the variance gets smaller. Earlier the variance is do you remember the variance of x bar 3 is 0.7. 0.7. Okay. Now you increase the n 10 times higher from 3 to 30. You expect the variance of bar 30 to be 10 times smaller than the n equal to 3, x bar 3, right? So you are seeing that it's from 0.72, 10 times smaller, 0.732, around that, 0.7. Okay, so this is the effect of a central limit theorem at play. Then next is following two, we approximate the sampling distribution by a normal distribution. Okay, approximate the sampling distribution by a normal distribution. Calculate the probability that average less than 2.5 months based on the normal distribution. Note the variance of a binomial random variable is number of trials times p times 1 minus p. Expected value is number of trials times p. Okay, Okay, first is histogram, mean value, variance. Okay, so this is one expected value. Okay, we'll start from here. Expected value is n times p. 10 times 0.3 is 3. So graduates per month. The variance is n times p times 1 minus p, which is 2.1. Okay, so the expected mean is 3 graduate per month. Expected variance, population variance is 2.1. Expected standard deviation is 1.449. Okay, so with that, we can construct what the normal distribution. So mean value standard deviation histogram. This is the histogram, population histogram. Use normal distribution to approximate the binomial population distribution. Okay, so if we apply sampling distribution by normal distribution, calculate this one. That's okay. Give me one moment. Standard deviation is this is a population mean. Standard deviation is this. Okay. So use normal distribution to approximate the binomial population distribution. Okay, so this is to show you the population distribution. Population distribution. So these two parts. Use the sampling distribution. Okay, next is approximate sampling distribution. Sampling distribution of mean following two. Okay, the sample size is 30. Okay, X bar 30. So these are X bar histogram sampling distribution of the mean n equal to 30. Okay, that's one mean of this from simulation, then variance 0.07, then from simulation. So now it's from theory. From theory, what is the mean value? Expected mean value based on theory is 3. 3 graduates. Then what is the theoretical variance of the sampling distribution? It is sample size 30, so you need to use a population variance divided by 30. So what is your population variance? Let's have a look at the population variance that we calculated earlier. It should be 2.1. Population variance is 2.1, right? 2.1. Then use 2.1 divided by 30. So this is the theoretical variance of sampling distribution of the mean, okay, when n equal to 30. Okay, then the standard deviation of the theoretical variance is square root of 0.07 is 0.2645. Okay, so now next is use normal distribution to approximate the sampling distribution of the mean. Okay, so here is first, let you have a look. This should be a theoretical sampling distribution. So now, with this, we are going to calculate how many calculate the probability. Okay, calculate the probability that average is less than 2.5. So 3 is here, 2.5 is here. So this is a sampling distribution. Again, this is sampling distribution because we are using the SD of this 0.0264, which is square root of 0.07. So this is using a normal distribution to approximate the sample distribution of the mean. Then it's a Q 2.5 is here. So the probability to the left of 2.5 and the mean value is EX mean, which is 3. The standard deviation is this, the theoretical standard deviation. So we want to calculate, use the P norm to give us the probability. So to the left of 0.5 is about 2.94%. Okay, 2.94%. Okay, good, 2.94%. So if you use Q norm, you put the probability there, it will give 2.5. So this is inverse. These two functions are inverse function. P norm is you provide the quantile value, or the X value. Then show me the probability up to that cutoff value. Then Q norm is give me the probability from the 0 up to a 2.94%. What is the X value? Okay, so I tell you this number of graduate. So relation and the progression to confidence interval of next week. So you are seeing that if we use Q norm 0.025, what is the mean value? Okay, mean value is 3. Okay, so um, if I want 2.5% to the left of this curve in this diagram, what is the number of graduates? It says 2.48 number of graduates. 2.48 number of graduates is here. Then to the left is 2.5. So next is I want from the right side, right tail to have 2.5. So I want area under the curve to be 97.5. So 97.5 to the left of the cutoff. What is the number of the graduate? It says 3.5. So 3.51. Okay, around 2.5 to 3.5. To the two sides, there will be 2.5% to the left and 2.5% to the right tail. Then what is in between these two range? It's 95% of the area. Okay, 95% of area under this curve. What are the two cutoff line? It is 2.48 and 2.35. So then we can say, okay, in between this range, we believe in the future we have 95% confidence the average monthly graduate, the number of graduates will be 2.48 to 3.51. Okay, so this is how we call a 95 confidence interval. So that will be the next week's content. Okay, thank you very much. That's the end of this today's week. It's long, and I hope you keep up the good learning. Okay, bye bye.